Hello. So we are now going to go over the last topic in Unit 1 on time domain signal processing. It's one of my favorite topics actually in all of signal processing. So it's something called convolution, which is a scary name. But all it is we're going to talk about mathematically how to represent echoes in audio. And sometimes people would call it reverb, so reverberation. So in the real world, sound bounces around and it comes back at different times from the things it bounced off of. So we hear many copies of the sound overlaid on top of each other. So let's start to do that with what we know, and then we'll talk a little bit more about convolution. So let me say I load this file here.
Oh my God, look, it's coming back.
Okay, so sound travels at 343 meters per second. So let's say that there was a wall, a big wall, 50 meters in front of me. Okay, and I said that there was a zombie walking towards me from that wall, and I said, oh my God, look, it's coming back. And the sound, I said that, somebody standing next to me heard that, but they also are going to hear the sound as it bounces back from that wall. Okay, so if the wall is 50 meters in front of me, the sound has to travel there and back, which means that it'll take actually 100 meters worth. So it'll be 100 meters over 343 meters per second. Okay, so that's the amount of time it will take for the echo to happen. So let's make this happen in code. So I'm going to make a new, well first, okay, so let me define, so delay time equals 100 over 343. We need to convert this into a number of samples that it happens. So what I'm going to do is I'm going to say t, that'll be the length of the echo in samples. That's going to be equal to the delay time times the sample rate, rounded down to the nearest integer. Okay, so now I'm going to make an array big enough to hold the original sound and its echo delayed. So I'll say that should be the length of x plus t. So okay, so up to, we have the original sound, the person standing right next to me. We'll assume that has no delay. But then we're going to have this echoed version. So I'll take out a slice that starts t samples in, and I'll go to the end, because I made just enough space for it. And I'm going to say plus equals x, actually, because it's going to get overlaid on top. So there will be times where I hear both the original sound and its echoed version. And maybe let's damp it down a little bit, because it loses some energy as it bounces off of the wall. Okay, so let's listen to that.
Oh my God, look, it's coming back.
So that's what it would sound like.
Oh my God, look, it's coming back.
So you can hear the reverb there, right? So a slightly delayed version of the sound. Okay, now you could certainly continue in this fashion. You could manually add each of the echoes like this. But there is a more convenient way to define this mathematically with something called a convolution. All right. So here's the idea, and actually I have a picture of this on our course webpage. So I'm going to look at this real quick. So this is convolution. So basically you have two signals at play with convolution. One of them is your audio waveform, so I'll pretend that that's the one on the top here. The other one is something referred to as an impulse response. The impulse response holds all of the echoes in it. So it's usually 0, but at the samples at which an echo would occur. So here, the echo occurred, let's see. Okay, here was 12,857 samples. So there would be a little 0.5 there. Because I'm saying 12,857 samples in, there's going to be an echo, and it's going to have a magnitude of 0.5. Okay, So here we're saying about 40 samples in, there's an echo with magnitude 2.7. Some of these are greater than 1, but mathematically, I just wanted you to see this. Okay, so this is representing all the information. So here there's 1, 2, 3, 4, 5, 6 echoes, all of slightly different amplitudes here. And all convolution does is exactly what we already said. It lines up the audio starting at each echo. Okay, so you shift the audio over, start it at the echo, and then scale it up by or down by how strong the echo is there. So you do that, you line these all up, and then you sum them together. And then you get this resulting audio waveform. Okay, so that's how that works. All right, now let's go back and see if we can do that, the same thing we just did, but using an impulse response instead. So doing convolution. So I need to make something that looks like this. That's going to represent my echo. So the convention is we often refer to this impulse response as H. So let me say H is equal to np.zeros t plus 1. So I'll say H of 0 is 1. Okay, so I'm going to have a copy of this starting at time 0. But I'm also going to have, starting at sample t, something that's 0.5. So let's just look at this real quick as a stem plot. That's a pretty common way to plot it. Although there's a bunch of samples, I guess it's going to take a second. So maybe that wasn't the best idea. Okay, but more importantly, let's... okay, yeah, I don't want to do that. Actually, if I plot it, that'll be good enough. Okay, so basically you see that there at sample 0 there's something, and then all the way back here there's something else. So that's my impulse response. It only has 2 copies. Okay, so if I say y is equal to np.convolve, so there's actually a method in NumPy that does this. np.convolve x h. We can listen, and we should get the same result. So here's the original that I did manually using NumPy slices.
Oh my God, look, it's coming back.
And here's the result I get using the impulse response.
Oh my God, look, it's coming back.
Same thing. So whoop-de-doo. But this makes it much easier to add more echoes. So let's say that I wanted to add a bunch of echoes. Maybe each, at some multiple of this time. So maybe I wanted to add 5 echoes. So what I can do is I can say, all right, fine, h of 0 is 1, but then I'll say h from t to the end in increments of t is equal to 0.5. All right, so let's just look at that impulse response real quick. So I'm saying, okay, I'm gonna have a bunch of lags. So actually there's gonna be, in about 1 1/4 seconds, there's gonna be actually 5 echoes now. Okay, now there's another command. NumPy's convolve's a little slow. I'm gonna use something called, something from the SciPy library. It's another library called Fft Convolve. It stands for Fast Fourier Transform Convolve. We'll talk about, it's very interesting, there's a connection in the next unit. We're going to talk about Fourier methods, and there's a way that you can, there's a beautiful algorithm that you can use to speed up this convolution if you use the Fourier transform. For now, we're just going to accept that there's a tool that's much faster than NumPy's version that's going to allow us to do this. And yeah, actually, if I waited for NumPy, it would take a long time, because now this impulse response, has almost 70,000 samples. Most of them are 0, so this is probably not the most efficient way to do it, because actually what's happening under the hood is that it's actually doing 0 times the signal plus 0 times the signal. So there's a lot of wasted computation here. But anyway, okay, so let's listen to this. So it should be 5 echoes.
Oh my God, look, it's coming back.
So yeah, that was that. Maybe we make the echoes get a little weaker as we go on. So maybe let's say 0.5 over 1 plus. Or you know what? I could just say h is equal to h over np.a range h or length of h over 40,000. or over the sample rate. So just to show you, so the echoes are getting a little weaker as they go on. Actually, maybe I want them to get even weaker, so maybe I'll do exponential. So say h times mp.exp negative mp.a range length of h over sample rate over 2. Let's look at that. Okay, so they're getting pretty weak towards the end. So let's listen to this.
Oh my God! Look, it's coming back.
Okay, so that's kind of a cool effect. So we're getting this reverb that fades out. So you can kind of see the potential here. All right, now before I talk too much more about the musical aspects of this, I want you to just do a quick exercise making one of these impulse responses, and then we'll move on.